Dry ice is born when we subject carbon dioxide to an extreme process of pressure and cooling, so intense that the gas, which is normally invisible and intangible, ends up transformed into a frozen, compact, silent solid. It's almost like taming a rebellious gas, so it adopts the form of a fleeting mineral. And when that white block comes into contact with water, the magic happens. A dense, white, serpentine cloud rises from its surface, lifting as if it had a life of its own. It slides across the floor, slips through cracks, flows down stairs, and can reach corners that even cleaning machines fail to touch. The scene seems straight out of a science fiction film, but behind that visual spectacle lies a surprising engineering process. And the big question is, how is this material produced on an industrial scale? Today, I'll take you behind the scenes, into the industrial heart where one of the most versatile and fascinating compounds of the modern world is born. The origin of dry ice dates back to 1835, when the French chemist Adrien Jean-Pierre Théolery conducted an experiment that appeared routine. By releasing liquid CO₂ from a pressurized container into the atmosphere, he observed that most of the gas evaporated instantly. But something unexpected remained, a white solid residue, cold as marble, yet much lighter. That discovery, initially almost anecdotal, ended up becoming the basis for a new type of refrigerant. In the following decades, that ice that didn't get things wet began to be used for an essential task in the 19th century, preserving food during long journeys, especially meats, fish, and dairy products that previously spoiled easily. Its advantage over traditional ice was obvious. It left no water or odors, and its temperature was far lower. Its importance grew even more in the 20th century and reached a decisive point during World War II. In a context where every minute and every resource mattered, dry ice made it possible to keep blood, medicines, plasma, and vaccines in proper condition even on the most remote fronts. It was a portable refrigerator at a time when cooling systems were scarce, fragile, and difficult to transport. What made it so useful was its unique physical behavior. Instead of melting like normal ice, solid CO₂ sublimates, going directly from solid to gas without leaving liquid residue. This prevented puddles, corrosion, moisture, and microorganisms that could damage critical materials. In addition, its temperature of -78.5 degrees Celsius made it the perfect ally for any mission where life depended on extreme cold. Today, nearly 2 centuries later, dry ice continues to play fundamental roles. It is part of daily life in laboratories, hospitals, transportation systems, and special effects. It keeps organs cold for transplants, such as hearts that must travel thousands of kilometers without losing vitality. It ensures the stability of sensitive vaccines and preserves biological samples that cannot tolerate even a 1-degree deviation in temperature. And, of course, it is used to create that mythic thick cloud we see in concerts, theater, cinema, and theme parks. Just submerge it in hot water and the CO₂ is released explosively, creating an immediate visual spectacle. But how is this material created industrially? To find out, we visited an Air Products plant, one of the global giants in the production of dry ice and industrial gases. The process begins with something essential: obtaining pure CO₂. Although carbon dioxide seems to be everywhere, obtaining it at the quality required to transform it into a solid demands a specifically controlled source. One of the most common ways of obtaining it is the fermentation of sugars during alcohol production. In breweries, distilleries, and wineries, CO₂ is released naturally as yeasts transform sugars into ethanol. The same occurs in the manufacture of ammonia, a key input for the fertilizers that sustain global agriculture. Likewise, carbon dioxide appears at various stages of petroleum refining and in industrial processes that release residual gases. It can even be captured directly from emissions of power plants that operate with fossil fuels, turning a climate-warming waste into a useful resource. However, the CO₂ from these sources does not come clean. It usually contains traces of oil, vapors, organic compounds, and solid particles. Therefore, before it can be converted into dry ice, it undergoes thorough purification. The gas first passes through mechanical filters that trap large particles. Then it moves through washing towers, known as scrubbers, where unwanted compounds, chemical residues, and contaminants are removed, all of which could affect the quality of the final product or damage equipment. This stage is critical. Insufficiently purified CO₂ would not only produce low-quality dry ice, but could also pose a risk in medical or food applications. With the gas cleaned, one of the most spectacular phases of the cryogenic industry begins: compression. Carbon dioxide is subjected to pressures close to 15 bar, equivalent to diving 150 meters underwater. This pressure forces the gas molecules closer and closer, dramatically reducing its volume. The next step is cooling, which brings the temperature down to around -20 to -30 degrees centigrade. Under these conditions, CO₂ takes on an intermediate state, a cold, dense liquid, much easier to handle and more efficient for storage and transport. That liquid CO₂ is stored in giant cryogenic tanks, capable of withstanding both low temperatures and high internal pressure. They are made of stainless steel to resist corrosion and have insulating layers that minimize energy loss. Each tank features safety valves, temperature and pressure sensors, and automatic mechanisms that relieve any risk of overpressure. These structures are true industrial colossi. They can store up to 2,600 tons of liquid CO₂, ready to be transported in tanker trucks or sent directly to the dry ice production line. When carbon dioxide finally reaches the machines responsible for bringing dry ice to life, one of the most delicate and fascinating moments in the entire production chain begins. The CO₂, until that moment kept in liquid form inside cryogenic tanks, is carried through insulated pipes to a controlled expansion system. There, its pressure is reduced to about 5 bar, a carefully calculated value designed to trigger the exact reaction the industry seeks. This sudden drop, almost like a fall into a vacuum, initiates an instantaneous transformation that can only be described as a burst of cold. In less than a blink, the liquid CO₂ expands so rapidly that its temperature plummets. The cooling is so violent that part of the carbon dioxide turns into an extremely fine solid, an ultra-frozen snow made of millions of microcrystals. Everything happens in fractions of a second. As it loses pressure, the CO₂ needs energy to stabilize, and it draws that energy from its immediate surroundings, stealing heat from everything around it. This theft causes a drastic temperature drop that freezes a portion of the gas, while the rest returns to its gaseous state and is immediately redirected into special conduits to be recovered, filtered, and reintegrated into the production cycle. Nothing is wasted. The cryogenic snow that forms does not fall chaotically. A collection chamber, designed like a sealed and perfectly insulated capsule, receives it under a constant flow. The result is a white, silky cushion, so fine that it resembles freshly fallen snow on a winter dawn, the kind that barely makes a sound when it touches the ground. However, this CO₂ snow is still a fragile, loose, and unstable material. To become something useful, a block, a cylinder, or a pellet, it needs to be compacted and shaped with tremendous force. This is where hydraulic presses come into play. Robust, reinforced steel machines capable of exerting pressures that defy human intuition. The snow is placed inside a rectangular mold, and a piston begins to descend with a pressure that can reach 300 bar. To visualize it, it's as if we placed a small car on a surface the size of a shoebox and then multiplied that force several times. Under such intensity, each CO₂ microcrystal fuses with the others. They are no longer independent particles, but a solid, uniform, dense frozen body. The result? A compact block whose temperature remains fixed at -78.5 degrees Celsius. Once pressed, the block is released from the mold with a sharp, precise motion. Then it moves on to mechanical blades that cut it to the dimensions requested by each client. Some require large blocks, others prefer smaller formats, and certain industries need sheets or pieces designed to fit inside specific equipment. But if pellets are what's needed, the process takes a different path. Instead of rectangular molds, the snow is directed to an extruder equipped with a perforated die. A piston pushes it with tremendous force through precisely calibrated holes. From that pressure, dry ice cylinders, pellets, are born. Depending on the diameter of the perforations, 16-millimeter pellets are produced, very popular in refrigerated transport due to their slow sublimation, or mini pellets of just 3 millimeters used in cryogenic cleaning. These mini pellets function like tiny projectiles. They strike the surface being cleaned, instantly freeze the dirt, and dislodge it without leaving any residue, since they sublimate on the spot. Once formed, blocks and pellets share a common enemy: time. Dry ice is always sublimating, always trying to disappear. This natural tendency requires it to be handled with great care from the very first moment. Larger pellets are placed in insulated containers designed to minimize any heat transfer. The roughly 3-kilogram blocks, more stable yet still delicate, are moved along another storage line. Throughout this phase, the plant recovers the gaseous CO₂ being released and reintegrates it into the circuit. This is not only an economic decision, it is an environmental responsibility. In the next stage, a conveyor belt transports the dry ice to the quality control area. There, specialized technicians perform a complete series of tests. It's not just about weighing and measuring the blocks. Their density, uniformity, mechanical strength, and even their smell are analyzed to rule out any contamination from the industrial environment. Exact dimensions are verified, internal fractures are checked for, and the purity of the CO₂ is certified. Only the products that pass this meticulous inspection receive approval to move forward. The next obstacle is the inevitable sublimation. At room temperature, dry ice can lose between 5% and 10% of its mass per day. This makes packaging a crucial step. The blocks and pellets are placed inside large thermal boxes made of insulating materials, such as reinforced polystyrene or multi-layer composites that slow thermal transfer. Their purpose is simple: to keep the cold trapped and preserve the solid CO₂ for as long as possible. Before sealing the containers, they are cleaned and inspected. Each box must be free of moisture, dust, or particles that could accelerate sublimation or compromise the product. Only then are the blocks or pellets inserted, ready to travel without the need for electric refrigeration. The extreme cold is preserved thanks to the same physical laws that created it. Finally, the dry ice enters the distribution circuit where its versatility shines. The food industry uses it to transport meats, ice cream, fish, and products that must remain frozen without interruption. Hospitals and laboratories rely on it to preserve ultra-frozen vaccines, biological samples, and organs that require critical temperatures. Industrial cleaning companies depend on the small pellets to remove dirt without generating secondary waste. And the entertainment world continues to rely on it to create foggy atmospheres, immersive visual effects, and dramatic scenes in concerts, theater stages, and film shoots. Thus, what began as an invisible gas ends up becoming one of the most extraordinary materials of our era, capable of crossing borders, sustaining life chains, driving industries, and creating illusions that seem drawn from a cold, white dream.